Hi guys and welcome to Study Project. Today we are covering International A-Levels A2 Physics Unit 4 and the topics today are momentum conservation, resolving vectors, impulse, and circular motion. So let's get into it. Our first heading is conservation of momentum. So what is conservation of momentum? It is when the momentum before and after a collision is the same in a closed system with no external forces acting. An external force can include friction. So what are some equations that relate to momentum? These include impulse equation, kinetic energy of a non-relativistic particle. A non-relativistic particle is a particle that does not travel near the speed of light. We have the conservation of momentum equation and we have the normal momentum equation. So the momentum unit is kilograms meter per second. So this is a common question that can be asked, where it asks how to use the apparatus to verify laws of momentum conservation. The apparatus include gliders, air track, light gate, cars, and a stopwatch. So look at the image carefully and you can decide how exactly you can verify the laws of momentum conservation. So how to use the apparatus to verify laws of momentum conservation? You should answer like this. So you want to measure the mass of each glider using a top pan balance, measure the length of the card on each glider using a rule, measure the time taken for card to pass the light gate, calculate the velocity of the glider by doing distance divided by time, or the length of the card divided by time taken for it to pass the light gate. Then you want to use the momentum equation, calculate momentum before and after the collision. And then you want to compare the momentum before and after collision and then determine whether it verifies the laws of momentum conservation. So why do we use an air track? We use an air track to remove friction, so we remove the external forces, so we can make it a closed system and to help prove that momentum is conserved. Another question that is common is when moving, empty fuel tanks are ejected by explosions, which increase the speed of the probe. Discuss whether conservation of momentum and energy apply here and why the speed of the probe increases. So you should answer like this. Conservation of momentum and energy apply here because space has a system with no external forces, making it an ideal closed system. After the explosion, due to Newton's third law, the tank and the probe will move in opposite directions with equal opposite forces. Both probe and tank will experience equal change in momentum due to momentum conservation, and the space probe now decreases in mass due to losing the tank mass. So speed increases so that energy is conserved. Also, there is chemical energy that is converted into kinetic energy, and this also increases the probe's speed. So this is a common question, and although the context may be a bit different, the overall way to answer it is the same. On to our next heading, resolving vectors. So what are vectors? These are arrowheads that represent magnitude and direction. And what are some rules to resolve vectors? If there's an angle, we use trigonometry, sine or cos. You want to label all the horizontal and vertical components and keep in mind the direction. This means that let's say you have an arrow facing upwards and then you have an arrow facing downwards. You want to label the arrow facing upwards positive, for example, and because it's facing upwards and it's positive, the downwards one would have to be negative because they're not traveling in the same direction. And then you want to make all the horizontal components equal to each other, and then you want to make all the vertical components equal to each other. So let's give an example now. So here we have a red ball and we have a green ball. As you can see, the green ball has 0 initial velocity while the red ball has an initial velocity of VR1. When they collide, the red ball and the green ball, they move in different directions based on the angle. You can see that the angle is different for both of them, theta 1 and theta 2. As you can see, after this, they both have their own final velocity. And after this point, we want to work out their horizontal components and their vertical components. So as you can see, the VR2 sine theta is the vertical component, and it is a sine theta instead of a cos theta because it is on the side opposite to the angle. Remember, sine is opposite divided by hypotenuse, and VR2 cos theta is the horizontal component where it is next to the angle but is not the hypotenuse. So again, this represents the horizontal component. Both the horizontal components for the red ball and the green ball are both still traveling the same side, and so they are both positive. However, the red ball and the green ball aren't traveling the same direction vertically. The red ball is traveling upwards and the green ball is traveling downwards. That's why the green ball in this sense is a negative. Now onto a challenge question that involves resolving vectors and momentum. So as you can see, there's a red ball with a mass 20 kg that travels at 45 degrees with a velocity of 15 meters per second. And as you can see, there's a blue ball that travels horizontally with a velocity of 8 meters per second. You can see this is the before the collision, and you can see after the collision that they join together and then they travel at a final velocity and an angle that we do not know. That's what we have to find out. So first thing you want to do here is you want to resolve the vector. You want to label the vertical and horizontal component. As you can see, I have done for the red ball and I have done for the final product. You see there's a 15 sine 45, 15 cos 45. And then you can see for the after collision, there's v sine theta and there's v cos theta. I used v because we did not know what the velocity is, and I used theta because again we don't know what the angle is. These are things that we have to find. So first things first, you want to write out your conservation of momentum equation. Although this is time consuming, I can assure you that it is worth doing because otherwise you will get mixed up. So you want to write for horizontal and for vertical that momentum before is equal to momentum after. As you can see, the red ball and the blue ball's mass are added together because they are joined together, so they are considered to be one particle. On to the next. I use the horizontal component of the red ball multiply with the mass of the red ball, and then I found the momentum of the blue ball, which I did the horizontal velocity of the blue ball multiplied with the mass of the blue ball. So this is the total momentum before the collision, and then to work out the momentum after the collision, we have to add up the masses, which is added up to be 370 multiply with the horizontal velocity component, which is v cos theta. So that's our first equation. Keep that in mind. Then is the vertical one. So this one, I took the vertical velocity component of the red ball and multiplied it with its mass, and then I found out the momentum of the blue ball, so I did the mass multiplied by the vertical velocity component. However, the vertical velocity component is 0, and so the momentum of the blue ball at vertically is 0. Again, the vertical component for the final product is the same as horizontal because we don't know what theta is and we don't know what velocity is. So this is our second equation. These are the two equations that would be very handy. The first one comes from the horizontal component and the second one comes from the vertical component. So let's start off with the vertical component. This way you can answer it simultaneously, but I did it by substitution. So again, do whatever works for you, but this works for me. So as you can see here, I moved the 370 to be divided by the 3012.132 equals to the velocity cos theta. I worked this out to be 8.1409, and then I worked out what v is by dividing that value with cos theta, and then I brought this value to be substituted into v for the vertical component side. This side we brought this 370 to be divided by 212.132, which I worked out to be 0.5733 equals to v sine theta. As we know, v from our rearranging is 8.1409 divided by cos theta, so I sub this in, multiply with the sine theta. As we know, sine theta divided by cos theta is tan, so that's why I changed it into a tan. Then we brought the 8.1409 divided by 0.5733 to equal to tan theta, and then I worked that out to be 4.03 degrees. And from this, I substituted 4.03 degrees into the theta, so I worked out the velocity to be 8.16 meters per second, and that's how you answer this question. So on to our next heading, impulse. What is impulse? Impulse is an impact force that is the product of force times time and is equivalent to the change of momentum. The equation is change of momentum equals to force times the change in time, and the units can be Newton second or kilograms meter per second, which is similar to that of momentum because again, change of momentum still the same equation, still the same unit. So here's an example question, very simple. So one golf ball was hit with a force of 1000 newtons for 0.1 seconds. Find the impulse. Force times time equals to the change in momentum. So you do 1000 newtons multiply with the time, seconds. So 0.1, which is equal to 100 newton second. Now onto the impulse force graph. So this is a tennis ball example, a tennis ball hitting a racket to be exact. As you can see in this graph, we have the time seconds as the x-axis and force newtons as the y-axis. And you can see that the area under the graph is impulse because remember, force times time is impulse. I labeled each part 1, 2, 3, 4, and I will explain each part and why the graph looks like it does. So when the ball is first hit, there's not a lot of force because there's not a lot of contact between the ball and racket yet, as there's barely any compression. That's why there's a slow increase, but as you can see, as time goes on, the force increases, and this is because the compression increases and so the force increases. And at number 2, this is where max compression occurs, so this means there's max force. And number 3, the force reduces once the ball decompresses, so once the ball starts to leave the racket, this means that there's less contact between the ball and the racket. And then number 4 is when the ball just leaves the racket completely, so there's no compression, there's no force. And this is another graph, just simplified, but the black line is the original line, the red line and the orange line are new lines. So the red line represents a higher force force with lower contact time, and the orange line represents the same force but different hitting technique, which can lead to a longer contact time. On to our next heading, which is types of collisions. So we have two types of collisions. We have elastic collisions and we have inelastic collisions. So elastic collisions are collisions where the kinetic energy is conserved and objects in the collision will collide and move in opposite directions after the collision. They will not join together. And as you can see in the image above, this is a representation of elastic collisions where they collide for a second or so and then they bounce off each other in opposite directions. But for inelastic collisions, these are collisions where kinetic energy is not conserved. This means that objects in collisions will collide and stick and move together. On to our next heading, circular motion. So as you can see, this is a circle which has a sector cut into it and there's an angle labeled theta, and around it there's the radius labeled r, and s is the circumference. And this equation, theta equals sr, is quite an important equation as it will be needed to help rearrange and change other equations that can be used. As you can see in this picture, we have a circle with a curved line and a straight line. So the curved line is the red line and it is the angular velocity. And basically it is represented by this equation, omega equals to theta divided by time. But this can also change into another equation, which is omega equals to 2 pi divided by time. But how can this be? As we know, omega equals to theta divided by time, and we know theta equals to the circumference divided by radius. And we know the circumference is 2 pi r from the how to work out circumference divided by r. This means that theta is basically 2 pi, making the formula omega equals 2 pi divided by time. So basically it is the change in angle over time, and the units for this is radians per second. And as for the purple line, which is linear velocity, it is represented by velocity equals to change in displacement divided by change in time. It is a speed in a straight line, and the units for this is meters per second. Both are scalar, meaning that they only represent magnitude and not direction. Equations that link both types of velocities is the omega equals to velocity divided by radius. So how do you link them? So you start off with the angular velocity, where omega equals to theta divided by time. And remember, time is equal to displacement divided by velocity. And as we know, omega equals to the circumference, or basically another way of saying displacement divided by radius. Omega equals to displacement divided by radius, altogether divided by displacement divided by velocity. And when you divide something, you can multiply it with the reciprocal, which is what I did. And this is why both of the displacements can be cancelled, because they are opposite ends. And this eventually results in omega equals to linear velocity divided by radius. On to our next topic is, what is centripetal force? Centripetal force is a force that acts perpendicularly to the velocity of an object and is directed towards the center of rotation. Things that you have to note is that centripetal force is always provided by another force. For example, friction. It does not exist as a force by itself. And another thing to note is that centripetal force is not drawn on a free body diagram. And these are two equations that can represent centripetal force. So what is centripetal acceleration? This is when a mass travels around a circle with uniform circular motion. How do you find centripetal acceleration? So you can see in the image above, we have a circle that has a particle represented by a pink dot that travels from point 1 to point 2. Point 1, it is traveling at initial velocity, and point 2, it is traveling at final velocity. And as we know, acceleration is the change in velocity over change in time. And change in velocity is the final velocity minus initial velocity. And since we can take these arrows as vectors, we can substitute these arrows or these vectors into this equation, which is the arrow minus another arrow. But we can change the direction of the initial velocity arrow to the left instead of the right by plussing them together instead of minusing them together. And in this way, we can make a vector triangle where it is a tip to tail triangle, and you can work out what the resultant velocity is. And in this case, the resultant vector will be the change in velocity. As you can see, I drew with dots. This vector triangle is still a sector, and so we can use the radian rule for the sector, which is L equals to theta multiplied by R, and we can start to make a substitution. And so we do L equals to theta R, which basically equals to change in velocity equals to theta multiplied with the velocity. And from this, we have a substitution value that we can use. As I mentioned, acceleration is equal to the change in velocity divided by change in time. And so since we know change in velocity is basically equal to theta multiplied by v, we can sub this into the change in velocity part. And as well as this, we know that theta equals to circumference divided by r, which is radius. And so we sub this back into the acceleration equation, meaning we have an acceleration equals to circumference multiplied with the velocity divided by radius multiplied with the time. And because circumference divided by time, circumference is another way to say displacement, for example, particle, and displacement divided by time is basically velocity. And so we have acceleration equals to velocity multiplied by velocity divided by radius. So we have our final centripetal acceleration formula, which is acceleration equals to velocity squared divided by radius. So there are two equations for centripetal acceleration. We have acceleration equals to velocity squared divided by r, which is radius, and we have acceleration equals to omega squared multiplied by r, which is radius. So we start off with acceleration equals to velocity squared divided by radius. And remember the equation I mentioned in the previous slide, where omega, or angular velocity, equals to linear velocity divided by radius. We can rearrange this so linear velocity equals to omega multiplied by radius, and then we can substitute this into the formula. So then we have acceleration equals to omega r multiplied by omega r divided by r, and eventually we end up with acceleration equals to omega squared multiplied by r. Onto some fire questions. This can be a common question that comes up. This question states, a satellite mass 9,500 kg takes 91 minutes for orbit at height of 340 kilometers above Earth's surface. If Earth's radius is 6,400 kilometers, calculate angular velocity. First thing you want to do here is you want to draw out yourself a diagram of Earth and label Earth's radius, and then label the 340 kilometers above Earth's surface. And so first thing you want to do is you want to use the angular velocity equation. As mentioned, there's two equations for angular velocity. The first one is omega equals to theta divided by time, and remember omega equals 2 pi divided by time. Remember, time here is in seconds, so the first thing that we have to do is change and convert the units from minutes to seconds. So we do 91 multiply with 60 to get 5,460 seconds, and then we do 2 pi divided by this value, and we will get 1.2 times 10 to the negative 3 radians per second. On to the next, they want us to work out the linear velocity. For this one, we use the linear velocity equation, which is linear velocity equals to displacement divided by time, and again, displacement or circumference is 2 pi r. We want to work out what r is. To work out what r is, which is the radius, we have to know what r represents. And so r represents the distance from the center of rotation to the object. So this means that we have to add Earth's radius with the distance above Earth's surface, which is 340 kilometers. And so we add the Earth's radius and this distance, which equals to 6,740 kilometers. And we want to convert this into meters, so we have to multiply it with 1,000 to equal to this value here. You substitute this value in, and again, you have to convert the minutes into seconds, so 91 times 60, and then you get this answer, which is 7,756.17 meters per second. But you can adjust this answer to a specific number of significant figures depending on the question. So in this case, there are two significant figures, so the answer in this case would be 7,800 meters per second. On to the next one, we have acceleration. Acceleration, we use the formula acceleration equals to linear velocity squared divided by radius. And as we know, linear velocity is our answer above, and so we bring that down and we square that and divide it with the radius that we also calculated. This will equal to 8.93 meters per second squared. And finally, we have force. So force, you use the force equation, which is force equals mass times acceleration. The acceleration in this case is 8.93 meters per second squared. And so you do 9,500, which is the mass of the satellite, and multiply it with the acceleration of the satellite. And this works out to be to two significant figures, 84,000 Newton. Onto our final heading, tension on spring loop. As you can see in this diagram, we have a circle and we have a green dot representing a particle that travels in a circular motion. And as you can see, I labeled the direction of the velocity and the direction of the weight. Weight always acts towards the ground, towards Earth's center. So as you can see, this is the order of the strengths of the tension. It starts from tension 1 to tension 2 to tension 3. Tension 1 being the strongest. Why is it the strongest? This is because it works in the opposite direction to its weight, whereas tension 3, the weight and the tension works in the same direction. As you can see here, centripetal force is represented by this tension. And these are two equations that can be useful if this sort of question comes up. So tension 1 minus weight equals to centripetal force. But why is tension 1 minus weight? This is because tension 1 is much larger than its weight. This means that tension 1 prevents the particle from falling down, whereas tension 3 and the weight are added together to equal the centripetal force. And you have to note that tension decreases when velocity decreases. So this means that the bob of the pendulum will fall down if the velocity decreases too much. Thank you for watching, and stay tuned for more videos.